In this video, we'll solve the following problem. Show that there are no integer solutions to the equation x squared minus y squared equals 50. Okay, so this problem asks us to prove that there are no integers x and y such that the difference of their squares would give us 50. Okay, so we are not required or asked to solve this equation for these unknowns. All we are asked to do is to prove that there are no integers satisfying this relation. So to prove it, our proof is going to be a proof by contradiction. It's going to be an indirect proof. Let me say by contradiction. So in any proof by contradiction, in any indirect proof, we'll assume the opposite of what's stated. So let us suppose that there are integer solutions to this equation. That there are integers m and n such that m squared minus n squared gives us 50. Okay, so we assume the opposite of what's stated, go through logical steps without making any mistakes, and arrive at a contradiction. Well, that's the idea, at least, to arrive at a contradiction showing us that it was our initial assumption that was wrong, which would show that there are no such integers. Okay, in this case. Now let's just look at the left-hand side of this equation. Well, this algebraic expression of m squared minus n squared hopefully reminds you of the usual of this identity of this being equal to m minus n times m plus n. So this should be equal to 50. Now let's just realize that these two numbers has to have the same parity, meaning that they are either both odd numbers or both even numbers. So why is that? Well, it's because m minus n is the first factor and m plus n is the second factor, and notice that the difference of these two numbers is even. Namely, I can write n plus n as m minus n, and in order to get m plus n, I have to add twice n. Okay, so notice that these two factors, the first one m minus n, the second one is m minus n plus an even number. So this is an even number. Okay, this should be equal to 50. So since we are taking a number and then multiplying it by another number that we get from the first one by adding an even number, that means we have whatever the parity was, the first one's parity was, and the second one should have the same parity. Okay, so let me just say that if m minus n is odd, then so is m plus n, because we have written it as m minus n plus 2n. And similarly, if m minus n is even, then adding an even number to it results in another even number. Okay, so whatever these integers were, they have to have the same parity. They are either both odd or both even. What does it mean? If they are both even, well, if they are both odd, if let's say we have these two cases, A and B. If A is the case, then m minus n times n plus n, the product of two odd numbers should be odd. Okay, so the product of two odd numbers should result in an odd number. But the equation tells us that the result should be 50, which is an even number. But 50 is an even number. So in the first case, here is our contradiction, because we have seen that we have two odd numbers, we multiplied them and got an even number. That just cannot be. Okay, so what if B is true? What if the second case is true? Well, if m minus n is even, then both m minus n is even, that is divisible by 2, it's a multiple of 2, and m plus n is also even, divisible by 2 or a multiple of 2. So if we multiply two even numbers, each is divisible by 2, then the product should be divisible by 4. And I hope you already see the contradiction. The contradiction is that the product that we actually get, 50, is not divisible by 4, it's only divisible by 2. 50 is not divisible by 4. So in this case, we again reached a contradiction. So both cases, both possibilities for the parities lead us to contradictions, meaning that we had our initial assumption wrong, meaning that there are no integer solutions to that equation. So this concludes the proof.